Okay, I'm going to go into some detail here about wave mechanics and where the Schrödinger equation comes from. I did another video on section 1.1 of Griffith's Introduction to Quantum Mechanics, and sort of glossed over this part, so I'm going to go over it into more detail here. So a wave is going to be the motion described by anything that is, say, oscillating. So we can just draw a picture of this. Let's say I have some planet and it's going around the sun. It starts at position 0 here, and then at 90 degrees it is at the maximum position away from that initial position. Then it comes down another 90 degrees and it is back at 0. We go 90 degrees again and it's at the maximum position, but this time on the other side. So I'm just going to come down here and it's going to be down here. And then it goes another 90 degrees, and after that next 90 degrees we are back at 0 again. If I draw this out with smooth lines, I get what's called a sine wave. I'm arbitrarily calling it a sine wave because I said that it started at 0. I can do the same thing with, let's say I have some mass and it's attached to a wall with a spring. I can pull the mass away from the wall and stretch out the spring, and my mass will be at position here. And then if I let it go, the mass is going to bounce back and it's going to go there, and then the spring is going to compress and it's going to go further in, and then it will go back to the original spot, and then it will go to the point where it's stretched out again. I'm going to draw that a bit better. So I will, let's say I start here. Now I stretch out my mass to some point here, and my position is now here. I let it go, the spring is going to push it back to where it originally was, and then the spring is going to compress because it has some extra energy in it, and it's going to go to some position that is on the other side. So it's going to go from here to here, and then it will stretch out again. I will trace that out and I get the same sine wave. I can go ahead and graph that. So with respect to time, and I have some position x, I started off here. I went to some maximum amplitude away in 90 degrees, and then it went back again to 0 in another 90 degrees, and then it goes to a maximum position away in another 90 degrees. Gonna make that nicer. So that would be 90. This would be 180. This will be 270. Until finally we will have 360. In terms of radians, that is going to be a whole circle, is going to be 2 pi. That's going to be 3/2 of pi. This is just pi, and this is pi halves. If I take the derivative of any position versus time graph like this, I get a very steep derivative here, and it's positive, so it will have a maximum value. The derivative at this point here, at the peak, is 0 at 90 degrees. The derivative here is very steep, but it's negative. And the derivative here is 0 at the minimum. And then here at 360, the derivative is very steep and it is positive. I draw that again with smooth lines, and what I get is a cosine. So I have a sine, and then I have a cosine. My sine was my position versus time. So my position as a function of time was just x. My cosine was the change in position over change in time, so that would be the velocity. If I do it again, I get the derivative here is 0. The derivative here is very steep, but it's negative. The derivative here is 0. The derivative here is very steep, but it's positive. And the derivative here is 0. So I start out at 0 with 0. At pi halves, I'm at a maximum, the negative maximum, so at 180, I'm at 0. At 270, I'm now at the positive maximum, and at 360, I'm at 0 again. So it's a sine wave, but it is exactly opposite of my first sine wave. So that one was the slope of my velocity. So that one is my acceleration. So my position versus time graph, the slope of that gives me my velocity. If that was a sine wave, then my velocity is a cosine. If my velocity is a cosine, the slope of that cosine is a negative velocity sine. So if I have any equation to satisfy that, we're just going to call it equation U, and that U has some amplitude that's just some constant, so we don't really care too much about that, but we're just going to call it A. And then that's going to be sine, and then we have T, because it's a function of time, and I'm going to use radians because I like radians better. So I'm going to say there's a specific frequency T. My frequency comes from, if I look at any part here, let's look at our original position, the one in black. Here I'm rising through 0, here I'm rising through 0. The time it takes to go there, from 0 to 360 degrees, will be the time it takes to go here and around a circle 2 pi. That's called a period. And we can call it big T. So that's the period. So every wave is going to have some period. After 2 pi, or 360 degrees, that just repeats again. And then it repeats again, and then it repeats again. So this function is periodic. Now for convenience, we might want to think of that as a frequency. So if I had a period T, I could think of a frequency, which would be 1 over T, or period is 1 over frequency. This would be convenient to think of things in periods such as a year. A year is the period of the Earth going around the sun. It goes around the sun in 1 year. 1 year is the period. If I think about car wheels revolving around the axis, it's not so helpful to think about how many seconds does it take the car wheel to rotate 2 pi. It's more useful to think of how many rotations happen in 1 second. And that's what frequency is. So frequency is the number of cycles per second. So number of cycles or rotations per second. In terms of my mass on a spring, a period would be how long it takes to go from here to here to here, back to my original position again. You could also think about how long it takes my mass to go from here to here to here. It doesn't matter where we start looking at the period. It'll be the same either way. So I could do period from rising through 0 to rising through 0, or I could do it from peak to peak. Either way, it's still the period. It's not going to be any different. And as we can see, my period between my position and my velocity and my acceleration graph stays the same. So when I want to write out my equation inside my argument here, what I need to have is that at a specific period, this is going to have a repeating value. So I need to encode in this equation the fact that my u is going to have the same number at 0 as it is as whatever time it is at 2 pi radians. Now, I always forget which way this goes, but it is going to be so HF is energy. HF is energy, H bar omega, and that one's over 2 pi is H bar. So H bar over 2 pi F. So it is omega is F over 2 pi. So I use omega because it's more convenient. I think that's not right though. I'll work that out again more carefully. So energy of a photon is H times F, or we could write that as H bar omega. I know that H bar is smaller than H, and I know they're different by a factor of 2 pi. So h bar equals h divided by 2 pi. So I could write 2 pi times h bar equals h. And then, yeah, now I have to replace it in here. So I'm replacing h with this. There we go. And now we can cancel out our h bars. And we have that omega equals frequency times 2 pi, or frequency equals omega divided by 2 pi. So what that means is that for every factor of 2 pi, I get the same u out. Actually, for every factor of pi as well, but it can switch from being maximum or minimum. So now that we have our equation in terms of space, so that would be like u is a function of x equals, so u is a function of t. We're going to do t first. Function of t equals sine omega t. We're also going to look at u as a function of x next. Now if I take the derivative of u, du dt, that's where I get my cosine. Now to take my derivative, I have to take the derivative of the inside, that is omega, times the derivative of the outside, that is a cosine omega t. Now I want to take the derivative of that, so I'm going to take my second derivative. This is my acceleration. That's going to be derivative of the inside, so I get another omega times this omega, omega squared, times a times negative sine omega t. So my second derivative equals negative omega squared a sine omega t. But u equals a sine omega t. Now I'm just too lazy to keep writing out that sine wave, so I'm going to go ahead and replace this with u. So I get d squared u over dt squared, so du dt, second derivative, is going to equal negative omega times u. So my original function equals times the negative omega squared equals my second derivative. Or I could write it like this. I'm just going to divide both sides by omega squared, and I get du dt squared. Okay. That's with respect to time, and that's how every wave is going to behave. That's the change in position over change in time. We could call that the acceleration. But if we look at this graph here, and we look at our pictures again, we can see that this position, if I call this position 0, then it goes to a max position away from 0, back to 0, back again here. So as a function of space, my amplitude is also changing. So I'm just going to call that amplitude A again. And we have 90 degrees, or pi halves pi, 3 halves pi, and then we're going to have 2 pi. and then that'd come back again here. And now as a function of x, I will have the same exact thing happen with my derivatives. So we're not going to really go through it in excruciating detail again, except just to draw it all out here. So we have the exact same situation happen, where we can see that mathematically we have the same sine and cosine values. Except now we're looking at derivatives with respect to x, not with respect to time anymore. Also with respect to x, since it's the same exact function, we can see that the position at 0 and the position at 2 pi are the same as each other. That's a wavelength now. So every wave has a characteristic period, and it also has a characteristic time. So we called the time that it took to go from 0 to 2 pi, we called that the period. We have a characteristic space that it's going to take to go from 0 to 2 pi, the fact that it's the same. So to go from 0 to 2 pi in one wavelength. So that's our wave number. So k is our wave number. It's analogous to our period, except it's going to be in terms of inverse meters. And that's because if I write my function u, now it's a function of x. It has some amplitude, and it has a sine wave, and it's going to be x. So it's a function of x, so x has to be inside the argument of the trig function, the sine. Anything inside that sine wave has to show me what the periodicity of that sine wave is. It also has to have no units. So I can call that k, and that is going to have units of inverse meters. So if x is in meters, k is in inverse meters. So it will have units of inverse distance. This k is going to reflect the periodicity, just as the time t did. So, like for the period, we had that time, we could call it t, would be equal to 1 over f, which would be equal to 1 over omega over 2 pi, or we have 2 pi over omega. So my time t is going to be 2 pi over omega. For k, we have the same idea, except that k is going to be in terms of meters. What we need to have here for our conditions is that k equal to 0 has to be the same, has to give the same u as k equal to 2 pi. So just as t equals 2 pi over omega, k equals 2 pi over lambda. Oh, yeah. Now we can go ahead and take our derivatives. So we have du dx, that is going to be derivative of the inside, k, times the derivative of the outside is going to be cosine kx. And then we have our second derivative, and that is going to be a k times a k, k squared, a, and that will be negative sine kx. So what we get here is that our second derivative is equal to negative k squared times a sine kx, which is u. I can write that again. U equals negative 1 over k squared times du dx squared. Now if I just set those two u's equal together, we have that negative 1 over k squared du dx squared equals negative 1 over omega squared du dt squared. We can cancel out our negatives, or we can write them both on the same side of the equation as they did over here. So what I have here is, I don't have a c yet because we started way further back than they did, but I could wrap that all up into just one constant here. So I could actually just go ahead and solve this guy to just say that it has one constant. So I could either, let's write it all out on one side. So I'm going to go ahead and add this to both sides. So I get 1 over omega squared du dx. Oh, whoops. 1 over k squared du dx equals 1 over omega squared du dt equals 0. Okay, and then just to make our lives a little simpler here, we're just going to multiply everything by k squared, k squared, k squared, so that will just turn into 1 du dx squared 1 minus k squared over omega squared du squared dt equals 0. Okay, now we're almost ready to get started. So you'll notice they don't have k squared over omega squared, but if we look at the units of that really quickly, so k over omega, so we have inverse meters divided by inverse seconds. So wave number divided by frequency. So that gives us units of seconds over meters, which means that this is a velocity, an inverse velocity. Specifically, looking at this example, we're going to start with a light. So I'm going to be looking at energy, or an electromagnetic wave. So we're going to be looking at energy of light, and for energy of light, we will be using an electromagnetic wave where we will have E equals E naught e to the I k omega t. In this general form, since this is a light wave, my velocity is going to equal the speed of light c. So I can just write my general equation out here with 1 over c squared, where c is the velocity of the wave. Now our velocity of the wave, you might remember from high school physics, if not, that's fine, could also be written as, if you have, say, this wavelength, that wavelength is completed in this amount of space, and it takes this amount of time t. So that means that we have some space over some time t, that is distance over time, and that is velocity. They might have replaced your t with 1 over f. So we have the velocity is the frequency times the wavelength, which is exactly what we get here with k over omega. So velocity is the frequency times the wavelength.